Good afternoon. Today we'll be going through a continuation of our tree-based model series. Today we'll be talking about random forest classification. Random forest classification is a supervised machine learning technique that improves prediction accuracy by combining many decision trees. Instead of relying on one model, it aggregates results from multiple trees to make a final decision. As seen in the display, the process overview looks like a random sample of the original data being selected. This process is known as bootstrapping. Multiple decision trees are then trained independently. Each tree makes a prediction. The final prediction is determined by majority voting amongst the trees. Each tree sees slightly different data and features. The diversity reduces overfitting and allows the model to generalize better to unseen data. Random forest performance depends heavily on hyperparameter tuning. For example, increasing trees improves stability, while limiting depth helps prevent overfitting. In the hands-on example that will be going on over at the end of this video today, we'll be using some of these parameters on the screen, where you see N estimators for the number of trees, max depth for the tree complexity, minimum sample split, max features, and random state. Random forest models are powerful, but they trade interpretability for performance. They're commonly used when prediction accuracy is more important than model explainability. Some of our advantages that come with random forest classification include high prediction accuracy, the handling of nonlinear relationships, the model works with large data sets, the model is resistant to overfitting, the model handles missing values very well. Some of the limitations include less interpretable than single trees. Another limitation includes that these are larger computational cost. These are slower training because of many trees. Random forest classifiers are widely used across industries because they provide strong predictive performance with relatively low pre-processing requirements. Random forest classifiers provide a powerful balance between accuracy, robustness, and scalability, making them one of the most widely used machine learning models in modern data science. Some of our use cases on the screen include fraud detection, customer churn prediction, medical diagnosis, credit risk assessment, employee burnout prediction. Some of the areas where this provides business value is the ability to improve decision making, automate classification tasks, identify important predictive features. Decision trees provide interpretability but often overfit to data. Random forest improves stability by averaging many independent trees. Gradient boosting takes a different approach by building trees sequentially, where each tree corrects prior errors. XGBoost enhances this boosting approach through optimization techniques such as regularization and efficient computation, often achieving the highest predictive performance. A good mental model comparison is that decision trees learn once, random forest learns together, gradient boosting learns from mistakes, and XGBoost learns efficiently from mistakes. Now, together, we're going to walk through a hands-on example of a model being put into use. So what I have on the screen and what I've gathered is a student dropout data set. This data set includes items like student ID, age, gender, family income, internet access, study hours per day, attendance rate, assignment delays, travel times, some various features that go along with a student's information, with who are they, how have they performed so far, etc. We also have this classification column for dropout. So it comes with zeros and ones. Zeros being no, one being yes. So we start by bringing in all of our libraries. So we bring in pandas, NumPy, some different scikit-learn packages like our train test split, our classification report, our confusion matrix, our pipeline package, our one-hot encoder, standard scalar, our column transformer, random classifier, our matplotlib package for creating our visualizations, and Seaborn for also creating visualizations and using our visualizations. So we first load the data set into a data frame. We're then presenting the first set of headers on that data frame. Now here's where we're going to start exploring our data. So we're just going to first look at our categorical columns. So we're just saying X for X in our data frame column names if that column's data type is an object. And if it is not, our predictor column or our dropout column. So we're looking through here, and what we're looking for is distribution amongst the columns. So maybe are there more females than males? So in this term, we're talking about bias being one category being heavier than another category within a certain field or feature, right? So here we're looking at gender. We can see those are about even. Here we can see that there's some slight bias towards yes for internet access and less bias to no. We see that this is skewed towards no for our part-time job, and so forth throughout the columns, right? Throughout our categorical columns, we went through and did the same. Now we also did the same for our numerical columns. So we went through and basically got another list of our columns that are not object columns, and they are also still not our dropout column. So student ID we'll get rid of later. We don't need it, so we're just going to ignore that. Distribution of age, though, we can see that there is a what we'll call a multimodal because it seems to have two bumps here with a large starting to be in this 15-year-old age group, right, in this range, right? But for the most part, we're pretty normal. Now we can see here for family income, we have a skewness left, where there is a high amount of individuals in our data set who are at a family income of less than $50,000. Here we see another normal distribution for study hours per day for students. And then here we see a skewness right for attendance rate, and so forth throughout the rest of our numerical columns that we've analyzed. Now here's where we start with actually creating our model. So here we're using our column transformer that we got from scikit-learn. This is a part of creating a pipeline for our model. So we're creating multiple features within our model, where our model just handles all of our pre-processing, some of our other features there. Right, so one that we're throwing on in here is our column transformer, where we're going to transform our numerical columns with our standard scalar. So we're going to standardize those columns. We're then going to use our categorical columns, and we're going to perform one-hot encoding. We're going to ignore the unknown columns, or unknown values, and then here, so we're passing our number columns that we created above, we're passing our categorical columns we created above, and so forth. Now, here's our random Forrest classifier model that we established above. And then whenever we discuss in our PowerPoint about our different hyperparameters, this is where those come into play. So here we'll be creating 200 trees. We'll have a maximum depth of each tree of 3. We'll use random state of 42, and then number jobs of 1. So those are our hyperparameters that we discussed in the PowerPoint before. Now here's where we establish our pipeline, and we're placing in our random Forrest classifier and our column transformer. Right? So within our pipeline, we're going to have two steps. Our preprocessor, which is our column transformer, and then we're going to have our random forest model, which is the actual model doing the majority of the heavy lifting here. Now we're going to create our X and our Y, where we take out the predictor column, the column that we're trying to actually target, and that's going to be our X, so all columns other than our target will be our X, and then our Y will be our target column. Right? Perform our train test split, where we're giving 80% to the train data and 20% to the test data. We're then going to fit our model, or our pipeline, per se, to our train data. And you can see this is what the pipeline looks like. It actually is a very good package that comes with Scikit-learn, where you can see the contents. So if we look in here, our steps for our pre-processing, our transformer. So in our number columns, we can see what's taking place, so our student ID, family income, attendance rate, and so forth. For our categorical columns that are going through one-hot encoding, we see our gender, our part-time job, our scholarship, and our parental education. And then we can see the hyperparameters that are within those as well. Now we can see that breakdown a little bit further here as well if we see for our preprocessor. Then we look for our numerical columns, and we look at our categorical columns. We look at our standard scalar package, one-hot encoding package, and then our random forest classifier and the hyperparameters. So this pipeline is a good way of being able to illustrate what is exactly in the contents of your model. Now, next what we're going to do is we are going to run a prediction. So we're going to do y_predict, and then with our pipeline, we're going to predict with our X test. Then with our pipeline, we're going to make a probability prediction that we're going to be able to pass to our ROC AUC. Then we're going to make a classification report, confusion matrix, ROC AUC score. Right? So we're just going to go ahead, and we have not ran these since we've been on this talk, so let's go ahead and from the top we'll run them all. And we'll let those catch up to where we are. Looks like they're already caught up. Perfect, perfect. So we can see now from our classification report that we have 0.80, so 80% of our no's are predicted as accurate, 0.7% of our yes predicted as accurate, and we predicted 1,545 yes or no, and 455 of yes. Right. Now with our AUC score, just a reminder that with our AUC score, the closer to 1, the better. The more strong of a model we have. Right? That's an overall score that we can give to our model. Now, with our confusion matrix, we can see that we correctly predicted false positives, or true positives of, these will be true negatives, top left, true negatives of 1,508. We correctly predicted true positives of 88. So this performed fairly well, right? Our overall score of 0.799. Now this can of course be tuned up, made more accurate, work with our hyperparameters to adjust them, make them stronger for us, so where this AUC score gets higher, right? And then, so here's our ROC curve that we use to visualize how strong we are. So what we do is we plot a figure, then we pass our false positive rate, our true positive rate, and then given labels, and then a title, and here we are. From that, we can see our curve, our ROC curve, that is getting closer and closer towards 1. So with some more Tuning to the hyperparameters, we can get this fairly adjusted, get it closer up towards 1, and become a stronger model for use in production. Right? Now with that said, this pipeline feature that we used for scikit-learn within a production state, this is a fantastic way of including your pre-processing stages into your model itself. So those don't have to be ran separate, but they can run within the model. With that said, that is the end of this video. Thank you for joining me today, and look forward to next time.